Welcome back to the deep dive. If you thought our last deep dive into the world of industrial pipe specifications was complex, prepare yourself.
hmm
We are now diving into part two of this forensic examination,
hmm
moving beyond the simple straight pipe and focusing on the crucial components that allow engineers to actually build a functional system.
Right.
We are talking about the difference between moving water and moving high-pressure superheated steam in an environment that cannot afford to leak.
That's absolutely right. Our mission today is, well, it's a targeted exploration of the components that define flexibility, integrity, safety, and ultimately the lifespan of any industrial piping system. We're talking fittings and flanges.
Okay, let's unpack this and start right at the physical foundation, the fitting itself. So we're defining fitting simply as the components that execute those directional changes, the diameter resizing or the branching within a run of pipe.
And if you look at the supply chain, fittings come to the project via four primary manufacturing routes. They are either formed from plate or existing pipe material. They can be machined from prepared forged blanks. They can be classically cast using molten metal, or for lower pressure applications, molded from specific industrial plastics.
We need to focus on the metal side first, I think, because that's where the truly punishing high-pressure specifications reside. Can we start with the concept of manufacturing components from pipe material itself?
Sure. That manufacturing method is primarily used for creating long radius bends. These are produced either through a hot bending or a cold bending process. For example, hot bending might involve inducing a curve using high-frequency induction heating while the pipe is mechanically stressed. It's very precise and ideal for those large, gentle curves.
But when we talk about elbows, tees, and components that face really intense thermal and mechanical stress, we usually pivot to forging. So why is forging considered, the gold standard for high-integrity fittings?
Because forging is fundamentally about physical strength through structure. It uses intense pressure hammering or squeezing to achieve what we call plastic deformation of the metal blanks. If you can picture a cheap cast iron skillet versus a finely crafted forged knife, you get the idea. Casting leaves behind microscopic defects like voids or a loose structure. Forging eliminates those as-cast defects, and critically, it optimizes the internal microstructure, aligning the grain of the metal along the stress lines.
So it sounds like you're engineering the component at a molecular level,
Hmm.
and that results in superior strength and durability, right?
Absolutely. That's why the most critical components, elbows, flanges, tees, unions, couplings, and caps, are overwhelmingly forged.
Now, contrast that high-integrity method with casting. You mentioned cast iron fittings. Where do they fit in the industrial puzzle?
Cast fittings are simpler, created by pouring molten metal into a mold. They are really used for lower pressure or non-critical applications. For instance, non-malleable gray iron is mainly used in residential or commercial construction for sanitary and waste drains.
Okay.
You also have ductile iron, which is stronger and often comes flanged, and malleable iron, which is cast iron that has been heat-treated post-casting to make it tougher and less brittle.
So, once the fitting is manufactured and ready for the field, the entire specification pivots to the joining method. Moving into connection methods, the project specification dictates the choice for every single joint. This isn't optional, is it?
No, not at all. The joining method is a non-negotiable choice based on the fluid, the pressure, the temperature, and the size. We have four primary methods, and the decision tree for choosing one over the other is extremely technical.
Let's start with butt welding, which sounds like the most permanent and robust solution.
Butt welding is mandatory for high-stakes process and utility services, especially for pipe sizes larger than 2 inches. This is the definition of a totally force-locking joint, offering maximum resistance to leakage, and is rated for the highest operating pressures. We see this in critical lines for drinking water, raw industrial waters, and high-pressure steam.
But you mentioned the downside, which is a key technical trade-off,
Yeah.
the internal weld route.
That protruding weld route can be a significant disadvantage inside the pipe. First, it may slightly affect flow characteristics. Second, and maybe more critical for maintenance, it impacts the ability to use internal inspection devices, or PIGs.
Wait, pigs. For listeners unfamiliar, you mean the self-contained tools, the inspection or cleaning robots that are pushed through the pipeline to check for corrosion or debris, right?
Exactly. And if that weld route sticks out too far, it snags or damages the PIG, halting inspection. Furthermore, that protruding root creates a tiny turbulence point that can sometimes initiate corrosion over decades of service.
So if butt weld is for big, high-pressure, high-flow applications, the socket weld seems tailored for smaller, equally critical lines.
Socket weld fittings are designed for process piping under 2 inches that carry flammable, toxic fluids or high-pressure steam. Their pros are clear. They offer easier alignment and faster assembly than butt welds, they are leak-proof, and they avoid that problematic internal weld root protrusion.
But the drawback here is startlingly specific, hinging on a microscopic distance.
It's incredible. Socket welds cannot be used where erosion is a concern, and that's due to the mandated presence of a 1.5 millimeter recessed pocket between the pipe end and the fitting wall.
Wow.
If you have erosive fluids moving at high speed, that tiny stagnant pocket becomes a vortex, initiating rapid corrosion or erosion failure. It's a fundamental physical limitation of the design.
And during assembly, there's another precision rule, the expansion gap.
You must leave a 3 millimeter expansion gap between the pipe end and the socket before welding. This gap is necessary to accommodate the thermal expansion that occurs during the welding process itself.
I see.
If you don't leave that gap, the weld is under immediate, immense internal stress as it cools, leading to eventual cracking. That level of precision is truly humbling.
Finally, we have threaded fittings. These feel like the easy access option.
They are. Threaded fittings are severely limited, restricted mainly to utility services, and only under strict parameters. Pressure must be 10 bar or less, temperature 180 degrees C or less, and pipe size 2 inches or smaller.
The major benefit is installation speed without complex welding. But how often does that speed compromise the system?
Well, that's the critical compromise. Threaded joints offer significantly less joint strength and carry a much higher possibility of leakage compared to any welded connection. They are fundamentally a lower integrity joint, only justified by the ease and speed of field erection for non-hazardous services.
So we've covered permanent joints. But what if we need to open the system for maintenance? Perhaps replacing a critical valve, inspecting a pump, or swapping out a segment. That's where we pivot to the dismantling joint, the flange.
That's the perfect transition. Flanges are essential whenever you need a connection that must be dismantled for inspection, routine maintenance, or replacement. The system simply can't function without them. And let's look at the variety, because the configuration determines its purpose.
Starting with what is essentially a heavy-duty cap, the blind flange.
A blind flange is used to terminate or permanently close the end of a pipeline or a vessel nozzle. Crucially, because it's bolted, it provides quick bolted access to the interior of the line for inspection, which is impossible if you simply weld on a cap.
Now let's discuss the weld neck flange. This is the choice for high-stakes applications. Why is that?
The weld neck is the standard for high pressure, high temperature, or sub-zero conditions because it's fundamentally designed to manage stress. Its signature feature is that long, tapered hub. This taper minimizes stress concentration by distributing the mechanical and thermal stress away from the flange face and across the much thicker, stronger wall of the adjacent pipe.
Oh.
It's a sophisticated piece of physics designed to spread the seismic shock or thermal stress across the toughest part of the line.
It's the engineering equivalent of building a shock absorber right into the connection. That makes perfect sense. Now, the lap joint flange, or swivel flange, sounds like the maintenance stream.
It is. It is designed specifically for systems requiring frequent dismantling. The genius is that the flange can rotate freely around a stub end that's welded to the pipe.
Okay.
This allows for quick bolt hole alignment. You can similarly spin the flange to match the holes, making erection much easier, especially when dealing with large, heavy, and difficult to adjust piping runs.
Moving through the rest. Threaded flanges and reducing flanges. What defines their operational envelope?
Threaded flanges offer that benefit of assembly without welding, making them ideal in explosive or highly restricted environments. However, they are highly susceptible to leakage caused by thermal cycles or bending stresses.
So they have a weakness.
They do, and you often see engineers mitigate this risk by seal welding them after assembly, which, ironically, eliminates the original non-weld benefit.
And the reducing flange performs two jobs at once.
It does. It reduces the pipe diameter while also providing a flanged connection. But here's the critical operational detail. The flow must travel from the smaller side to the larger side. If the flow is reversed, the sudden increase in velocity and subsequent expansion will cause severe turbulence and potentially localized erosion right at the reduction point.
Finally, the orifice flange, which is all about metrics.
The orifice flange is strictly for measurement. It determines the flow rate by measuring the pressure drop across an internal device called the orifice plate. The assembly is unique because it includes specialized fasteners called jack screws. These screws are specifically built into the assembly to force the two flanges apart, allowing maintenance crews to inspect or replace that orifice plate without extreme manual force.
So the flange design and material get the liquid where it needs to go, but the specific contact surface, the face and the seal, the gasket, ensure the system doesn't hemorrhage its contents. Let's move to section 4, and the critical details of flange faces and gaskets. What are the three main faces?
They are the flat face, FF, the raised face, RF, and the ring-type joint, RTJ face. The flat face is completely level. It's used almost exclusively when connecting steel flanges to low-pressure, brittle cast iron equipment or valves.
Why brittle material specifically?
You need that full contact surface to prevent the intense bolting stress from cracking the cast iron face.
I see. And the raised face, or RF, which is the most ubiquitous.
The raised face has a small protrusion, and its purpose is simple geometry. It concentrates the entire bolting force onto the smaller surface area of the gasket, which guarantees a positive, reliable seal.
And the height is standardized.
Oh, precisely. It's 1/16 of an inch for Class 150 and 300 flanges, but it jumps up to a 1/4 inch for pressure ratings of Class 400 and above, reflecting the greater force needed for high-pressure sealing.
Then you have the ring-type joint, the RTJ, which skips the traditional non-metallic gasket.
Right. It relies on a heavy metallic ring that seats in a deep, machined groove. This is the choice for systems rated 400 psi and much, much higher. However, while robust, it creates maintenance difficulties. To dismantle an RTJ connection, the flanges must be forcibly separated to extract that ring from its groove, which can be a nightmare in cramped, confined installations.
Let's talk about gaskets, the consumables that complete the seal. Starting with full-face gaskets.
Full-face gaskets are typically non-metallic, often PTFE or graphite-coated, and primarily used on those flat-face flanges for low to medium pressure general services. Because they cover the entire surface, replacing them means the entire joint must be fully disassembled and separated.
And the complex spiral wound gaskets.
These are highly resilient. They consist of metallic winding, providing the structural strength, combined with a non-metallic filler, which provides the actual sealing element. They handle a massive range of temperature and pressure, and here's a fascinating detail for specifier. The color of the outer ring on the gasket is standardized by ASME B16.10 to indicate exactly which type of metallic winding material is used.
Now back to the metal-on-metal sealing of the RTJ gaskets. What is the fundamental, non-negotiable material rule here?
This is critical and purely mechanical physics. The RTJ's functionality relies on the softer metal of the gasket being compressed into the groove of the harder flange material, allowing it to flow and form a perfect seal.
Ah, so it has to be softer.
The absolute rule is that the gasket material must always be softer than the mating flange material. We see three main types: type R, oval or octagonal, type RX, interchangeable with R, and type BX, which is designed for the highest pressure systems where the two flange faces actually touch.
And one final type of gasket that addresses a chemical issue rather than a pressure issue: insulation gasket kits.
Their primary purpose is to stop galvanic corrosion. When you connect two dissimilar metals, say a carbon steel flange to a stainless steel valve, and add an electrolyte like water, you create a battery.
A battery, right.
The current flows, and one metal corrodes rapidly. These kits provide a complete electrical insulation of the joint to prevent that current flow. They come in full face, inside bolt circle for better centering, and specialized DRTJ kits for the metallic ring joints.
That brings us to section 5. Synthesizing all this detail into one single, defined master specification to fully describe a flange for purchasing and compliance, there are 5 mandatory categories of information needed.
That's how we group them. To specify a flange, you need 3 pieces of information that define its size and strength, and 2 that define its connection method.
Let's list them using that framework.
Okay, size and strength are: 1, nominal pipe size, NPS, governed by ASME B36 standards; 2, pressure temperature rating, which uses ASME B16.5 for flanged fittings classes 150 up to 2500, or ASME B16.1 for socket weld and threaded fittings classes 3000 up to 9000; and 3, material designations specified by ASTM standards like A105 or A182.
And the connection methods.
That's 4, N-types weld neck, socket weld, swivel, threaded, and 5, flange face FF, RF, or RTJ. You need all 5.
Here is the complete example specification we pulled from the source material for you. Flange 6, hashtag 900, RTJ, WN, share 80, ASTM, A105. Let's break that down piece by piece.
Okay. That spec means you are getting a 6-inch flange rated for pressure class 900. It uses the highest integrity face, the ring type joint, or RTJ, and it has a weld neck WNN type for stress management. It's compatible with a Schedule 80 pipe thickness, and critically, it is made of ASTM A105,
Which is.
the standard carbon steel used for non-corrosive process gas or utility piping.
And that material designation at the end is chosen based entirely on the service conditions.
Precisely. Carbon steel, like SA105, is fine for standard processes. But if you have low-temperature services, perhaps a freezing utility line, you must switch to SA350 grade LF2 to maintain ductility and prevent brittle failure.
And for corrosive stuff.
For services that are seriously corrosive or erosive, you jump entirely to duplex stainless steel SA182 grade F51.
Why duplex specifically?
Duplex stainless steel offers a combination of corrosion resistance similar to high-end stainless but with superior strength, which is essential when the fluid itself is constantly attacking the pipe wall. Likewise, produced water or freshwater lines often require cupronickel or B466 due to its specific resistance to marine and biofouling environments.
So we've covered everything from how you deform the metal blank to optimize its grain structure, all the way down to the exact material softness required to create a perfect metal-to-metal seal between the flanges.
The necessity of precision here defines the industry. The difference between a reliable, compliant system and catastrophic failure often comes down to that tiny 1/16 of an inch height difference in a raised flange face, or ensuring the correct type of insulating gasket kit is used to prevent the hidden menace of galvanic corrosion.